One thing that we went a little long in that one, so I sort of just cut it off. And then I looked at this and I said, you know what? We need to discuss this and at least just show you the movie, okay? For those of you who end up teaching astronomy, if you ever teach astronomy in your lives, the #1 way of charting the stars will be the Hertzsprung-Russell diagram. I sort of left it off because I was like, all right, but you need to see this movie if you haven't seen it, okay? There's a really cool movie that we've got here. All right, so what I talked about here, that we've got advanced star plotting, more stuff here. In astronomy, the fundamental chart of plotting the stars is magnitude versus color. Okay, the observed brightness of the star versus the observed color of the star. In theory, the magnitude is proportional to what we call the luminosity, the brightness of the star, and the color is proportional to the temperature. So there is the observer's diagram, which is called the color magnitude diagram, and then the theorist's diagram, which is temperature versus luminosity, which we usually refer to as the generic HR diagram. All right? And the point of this is that it shows you the classes of the stars, okay? And how I could justify putting this star charting exercise on a day when the science focus is supposed to be exoplanets actually is this diagram. Because this shows you the types of stars in the universe, which is actually also important for understanding the types of planetary systems in the universe. Okay? So, this is a plot of the HR diagram. All right? On the bottom axis, we have surface temperature, which, like many things in astronomy, is also plotted backwards. Okay? 3,000 degrees over here, up to about 30,000 degrees over here. All right? So, we're plotted surface temperature of the star there. You have spectral class OBAFGKM, working from left to right, which is also, which is the stuff I showed you, excuse me, drinking a Dr. Pepper here, which is what I showed you on the other day, corresponding to color, corresponding to temperature, okay? On the y-axis, we have luminosity going from, I can't read this one, it should be 10 to the minus 4, 10 to the minus 2, 1, 100, 10,000, and a million. 10 to the 6 up there. Logarithmic scale, okay? It's a log plot. Astronomy things vary by really, really large factors. We have to use log plots, okay? All right, but what happens when you plot temperature versus luminosity is you don't get a scatter plot. You don't get things falling anywhere on this temperature-luminosity plane, okay? You find that there is a line of stars that sort of that we call the main sequence, which means that stars can only exist with certain temperatures and certain luminosities. This line is the hydrogen burning line. All right, if you are burning hydrogen in your core and you have a certain temperature, surface temperature, then you will have you can pretty much predict what your luminosity will be. The temperature and the luminosity are correlated, okay? All right, that's what we see in this plot, that if you are a standard star that's burning hydrogen in your core, you fall along this line. You can't appear just anywhere in this chart. If, however, you progress beyond hydrogen fusion in the core, and you progress to helium fusion in the core, you run out of your hydrogen and you have helium fusion, then you move over onto this red giant branch over here. So helium fusion in your core, there is also a correlation between temperature and luminosity, but it is a different correlation between temperature and luminosity. Finally, if you go beyond helium fusion and you go into the other ones, you become supergiant, and supergiants all have high luminosity, but they can have any temperature, surface temperature, because these are variable stars that actually can change their size. They can actually get much, much bigger, much, much smaller, depending upon the star. You have your red supergiants, such as Betelgeuse. You have your blue giants or blue supergiants, such as Rigel. Okay? So when you get to the giant stars, they actually can have a range. Up here, the luminosity is more fixed and the temperature is changed. If you then blow off your outer layers in the planetary nebula, you reveal the core of the star, and that's called a white dwarf. The white dwarfs have a sequence over here. All right? So this is the fundamental plot of trying to understand the various types of stars in the universe. The other thing I want you to notice on this is that they've sort of plotted it in sort of a density function, that there are a lot more red dwarf stars than there are blue bright stars, okay? Like most things in the universe, the really big things are exceptional, and the really small things are ordinary and common, and the meek dominate the universe, okay? They don't just dominate the Earth, they dominate the universe. There's a lot more of these ones, and that's an important thing. Now, here's the fun thing, okay? This is a movie on constructing the Hertzsprung-Russell diagram using the globular star cluster Omega Cent. This is going to play nicely. Okay, so this is a movie taking a real Hubble telescope color image of the globular star cluster Omega Cent. And from it, we're going to show how the HR diagram naturally falls out. So this is that heavily colorized version of the Omega Centauri globular cluster, where the reds are redder than they should be and the blues are bluer than they should be because we're using ultraviolet and infrared light, but it works really well. So we zoom in here, okay? All right, let me pause. Let me just go back just a touch. All right. So we zoom in and we have all these stars, and they are a variety of colors. So what if we sort the colors, okay? So we're going to take the blue, take it to the left, and the red, take it to the right. And push play again. So simply, what we've got here is a diagram where we identified all the stars and we're able to manipulate them in a graphics program. Okay? Whoops. That's not supposed to happen. All right, we'll play that again. Sorry about that. I hit the wrong key. So in order to do this visualization, they identified every star in the image, they put it into a catalog, and then were able to then manipulate it with a graphics program. Okay, so the stars were redrawn using what a technique we call synthetic stars. All right, so now we have the bluest over here, the reddest over here. Now what we want to do is sort by luminosity. We sort it by color. Let's sort by luminosity. The brightest stars at the top, and the faintest stars at the bottom. Did that go? There we go. Take the brightest stars to the top, the faintest stars to the bottom, and boom, it just naturally falls out. Taking real data and showing how the diagram that seems so theoretical really pulls out from a Hubble image. All right, and we can identify the various things. That horizontal branch is actually stars in the transition going from red giants. They are unstable stars as well. They don't have any supergiants in this globular star cluster. And then we put everybody back where they are in their right ascension of the declination. So that is a transformation of a right RA and DEC picture into a temperature luminosity diagram. All right? Okay, so that's that. That's a lot of fun. That is accessible on the Hubble site webpage. I will also post it on our webpage, where that will include everything I show you this week. I plan on posting up on a webpage where you can download it and use it. Your tax dollars pay my salary, and as a thank you, I want to give you as many tools as possible to use in your classroom. Okay? So keep paying my salary, and I'll keep giving you cool things to use in your classrooms. All right. So that finishes our stars part of this, and we'll see how that plays in when we talk about exoplanets. All right. So we'll talk about going from planets to exoplanets. Your parents, we learned the solar system as the sun and 9 planets back when Pluto was a planet. Okay, the new solar system, we talked about this. We did this is why we did the Not Your Parents solar system stuff before. Okay, so usually in this talk I go through and I teach them the new version of the solar system, the Kuiper Belt, all right, and the Oort cloud, all right, on all that, the stuff I showed you this morning, talking about that. This is where we get to the 21st century solar system, sun, rocky planets, asteroid belt, giant planets, Kuiper Belt, and Oort cloud. Gives us this great organizational structure in which to understand our solar system, okay? But, so the organizational structure, I've not but yet, that gives you the classification, the structure, and the clues to its formation and evolution in as much as the rocks are in, the ice balls are out. That gives you a volatility gradient in chemistry. That's the way it has to go. So the idea is the nebular hypothesis that you get this big gas cloud, and this gas cloud collapses, all right? Any gas cloud that you try to create is going to have some net angular momentum. It's going to have a little bit of spin. Even if it's a giant cloud, there's going to be some net angular momentum. So when it comes down and gets really, really, really small, shrinks by a factor of 1,000 or 100,000 or a million, it's going to be spinning, right? You take pizza dough, you spin it in the air, what happens? It becomes a disk. You take a big cloud, you drop it in, it's going to be spinning, it's going to become a disk, okay? This is the nebula hypothesis. You collapse a nebula, you get a spinning disk at the center. At the very core is going to be the densest thing, and that's going to be where your star is going to form. Material to build the star may come from a cloud, but it's going to feed onto the star through a disk. So this disk is a fundamental process of star formation, but since you've got this disk of material, stuff in that disk can slam together, collect, and agglomerate into objects around that star, and we call those objects planets. So we get the disk, and then we have the planetesimal hypothesis that the small things slam together to form bigger things, the big things slam together to form even bigger things, and so on. Actually, what turns out is you get objects the size of the moon relatively easily. If you do the chemistry from, the forces that can stick, tiny dust particles together all the way up, you get to the moon. Once you start getting to the moon, when things smash together, they have a tendency to also break apart. So getting things larger than the moon is difficult. You can do accretion onto that. For the giant planets, you can accrete a rocky mass and then add gas onto it for the gas giants, or add ice balls onto it for the ice giants, Uranus and Neptune, all right? Important for that is that at some point out in this getting away from the sun, ices can develop, all right? So you have an ice line out here, okay? The other thing that we know is that Jupiter and Saturn and Uranus and Neptune probably did not form in the places that they exist today, all right? There will be some angular momentum transfer between the objects in the disk, and the big things tend to move in towards the sun, the small things get kicked out, okay? Something that takes an entire semester of graduate school to learn can be summarized in one statement. Mass goes inward, angular momentum goes outward. So the big guys move towards the center of the system, the small guys get kicked out, which is why we believe that as Jupiter migrated inward, the ice balls, the comets, got kicked out and become the Oort cloud, right? That's where we get the Oort cloud, from Jupiter's migration inward. Jupiter and Saturn migrated a bit inward, okay? Uranus and Neptune probably migrated, although in their case, I'm told that they might have actually migrated outward, and I'm not sure I fully understand that. But I'm not a stellar planetary system dynamicist, so that's still a little unsure in my head, okay? But the point is that we do expect that the giant planets do migrate by angular momentum transfer, basically kicking things around the solar system, which also means that there would have been a lot of chaotic things flying through the solar system, which shows up on the moon and all the other bodies that we've seen with lots of craters. Okay, by measuring the dates of craters on the moon, we see a heavy bombardment era. that such that there was a lot of crashing and things around. So you can see how our understanding of the formation of the solar system explains lots of the features that we see in our solar system. A nice disk, a nice orderly rocks in the middle, ice on the outside, lots of craters around the solar system, lots of planetary, a little bit of planetary migration, comets out at the edge of the solar system. Isn't that a beautiful picture? Don't we feel happy? All right, we can explain our solar system. Great! But, well, our solar system is just a category of one. Are we ever happy with when we have a category that has one object in it in science? Well, we've never had any other solar systems to study, so we couldn't help ourselves. Now we do. All right, and so this is what this talk is about. How do we then generalize our ideas about our solar system to other solar systems, okay? So I have no idea what I'm supposed to say on this slide here. Oh, I'm talking about Orion, yes. Okay, so we're gonna take a look at the formation of other planetary systems, okay? And we're gonna use Orion. I use Orion a lot because it's a nice constellation. All right, so when we look at visible light, we see this, all right? However, if we add a hydrogen alpha filter to an image like this, and we look for the gas that's glowing in hydrogen, we actually see a really cool image like that. All right, so here is the stars Orion, and look at this red gas that appears around Orion. There is a huge gas cloud in the constellation Orion. It's called the Orion Molecular Cloud. It doesn't show up generally in visible light, but when you specifically look for it in hydrogen alpha, you see this huge loop here, all right? It looks like a half of a bubble. It's called Barnard's loop, all right? And the brightest thing down here, well, that's that Orion Nebula, okay? The Orion Nebula, the belt, the sword, the middle star of the sword is not a sword, it's not a star, it is a nebula. This is the Orion Nebula, or poetically, the Great Nebula in Orion. Very nice. And we zoomed in on that. Hubble took this amazing image here in 2006. We released this image. Actually, at full resolution, there's about 1 billion pixels in this image. I, of course, can't show it to you with this projector. Or if I did, it would take quite a while to zoom in and zoom in and zoom in. But if we go in close, we can see that the Orion Nebula has these 4 bright stars at the center of it. They're the trapezium stars. There are some big, hot O stars. These are big and bright, and it's their ultraviolet energy that sweeps across the nebula, heating up the gas, causing it to glow. But let me go back to a Hubble image from 1985, which has a little bit better contrast, where those stars don't blow out everything, taking in some different filters that help us see things more clearly. And we then zoom in on those 4 stars, the trapezium, 1, 2, 3, 4. And in this image, because the contrast is better, we see some really funky things going on. What do you think that is? A what?
Oh, I just said it's a jellyfish.
It's a jellyfish, okay. Some people, jellyfish is a good term for it. Does it remind you of anything else? Comet, okay, right? Astronomers who first looked at this said it looked like a tadpole. All right, or some astronomer somewhere said it looked like a tadpole, so they nicknamed these things tadpoles. And you can see that there's not just one tadpole, there's another one here, or more jellyfish here, and more jellyfish here, and a jellyfish there, and a jellyfish there, and a jellyfish there, and they all seem to be pointing toward the big bad guy in the center, Beta Orionis 1c. Okay, Beta Orionis 1c is the name of that star. That is the largest star in the Orion Nebula. It has the largest ultraviolet radiation, and it has the largest stellar wind. We talked about our sun having a stellar wind that blows across interplanetary space. This stellar wind blows across interstellar space. And the wind blows back like a windsock the material around these other forming stars. All right? So there are newborn stars around this really big bright star where the material is being blown back by the stellar wind. You'll notice they are bright on the near side because that's where the ultraviolet radiation is hitting them, and then have the tail on the side away from them. There are a bunch of these guys all around. And what we believe is going on inside there is that a star is trying to form, and that nebula, the finish of that nebular hypothesis is getting blown away. And if you form your star too close to a giant star, it may get rid of your material before you have a chance to finish forming your star and your planet. So you might get a diminished amount of material on the star and perhaps a diminished amount of material on the planet. That's a hypothesis that hasn't been proven yet, but it certainly seems like some material at least is getting blown away from these systems. But if you go further away, you find things that don't have these windsock shapes. They actually have this sort of black line shape. And it looks like there's a scratch in the negative. But this isn't the negative, it's a digital photograph. All right, and it's actually a disk seen edge on. And here you can see one where there's a star peeking out of the center, and here's one where you definitely see the star at the very center. This is confirmation of that nebular hypothesis where there's a disk around a forming star. Okay, we are seeing star formation and planetary disk formation in the Orion Nebula. And this may not seem like really news, but 20 years ago, these were the first images to show us in a star-forming region this process going on, right? Where we're actually confirming this idea. Now, basic physics tells you angular momentum's conserved, you've got to have a disk. But until you see it, you don't know, all right? You can't say for sure. So that is what we saw. All right, so we have, thinking about disk, we have a face-on view of the disk. We have an edge-on view of the disk. All right, and so there would be a star forming in here, and then you would have planets forming in rough circles around that. All right, so you have to get in your mind the different geometries of what you might see, and that it can have many different orientations across it. So I'm going to show you a bunch of pictures, start to apply this model of a disk with a star at the center and rings around it for planets to various of these images. Okay? One other cool thing we've got, and it's not playing. Oh, John, were these the ones that didn't play?
Windows media file.
Okay, so it's a Windows media file. I didn't fix that since last time. I'm sorry, folks. Let me skip that one because that's a cool movie. I'll show you a cool version of that movie tomorrow. Okay. All right. So basically, that's a 3D fly-through where you spin around the star and you see things that are going on inside it. Okay. All right. But we have seen disks around lots of stars now. We're looking for lots of disks. So this is the star beta Pic, or what would be here is the star beta Pic. Again, we're blocking out the coronography. We block out the light of the star in order to see the faint stuff around it. On large scales, you can see a bit of disk when you block it out. You're able to get in close, you're able to see that there is a disk material. And this would be an edge-on disk in beta Pic. We followed that up very soon afterwards, a couple years later, and with other things, and where we start to see the details of this. And then with the STIS instrument, we were able to get in much closer to the star, block out the light of the star, and we see a very nice, thin, collimated disk across here. Beta Pic's disk is roughly very much edge onto us. All right. The cool thing about Beta Pic, however, was take a look at this bump here and this corresponding bump up here. There appears to be an extra tilt to the disk. There is a main disk here, but somewhat in the interior, it looks like there is some material bumping down and bumping up so that there is a second disk that's inclined to the first disk. All right? So that's something that we're still studying on Beta Pic, why there appears to be an extra inclined disk on it. But we are seeing disks around Beta Pic, and then if we use the Keck telescope in the infrared to look even deeper, and use adaptive optics in the infrared, which they work, where you can get really high resolution from the ground. You can see that there is the star in the center, but there's a clump of stuff about 15 AU away, another clump of stuff about 40 AU away, and another clump 65 AU away, where 1 AU is the distance from Earth to the Sun. Okay? So we're seeing clumps within the Beta Pic disk. This is exactly what we would expect to see if you were getting planet formation in the disk. Okay, we're starting to confirm this nebular hypothesis, this wonderful story that we tell ourselves. Okay, We also start to see other things even further out. HR 4796A, again, the star is blocked, but you see this ring of material, this beautiful ring of material. Here is the diameter of Neptune's orbit. All right, what does this look like? This looks like a Kuiper belt around another star. All right, I gotta say, Neil Tyson and I were at American Museum of Natural History when this image came out, and we were preparing our exhibits, and we were just talking about how we were going to handle Pluto and talk about the Kuiper belt. We were just discovering the Kuiper belt in our own solar system, and we looked at this image and goes, damn, that's a Kuiper belt in another solar system. So as we're learning about the new regions in our own solar system, we're starting to see things that look like that same region in other solar systems. So we're starting seeing structure. We're also in HD 141569. Most stars don't have pretty names, okay? Like Betelgeuse and Rigel. Most of them have it. We start to see, this is what Hubble sees when we transform the data as if we would see it edge flat face on. We can start to see concentrations in this disk as well. So we're seeing disks, we're seeing clumps in the disks, we're seeing all sort of spiral structure in this one. Again, we're seeing things in this. So let me just show you my two favorite ones. One is AU microscopy, where we see a beautiful thin edge-on disk. Here's the size of Neptune's orbit. And then this one, which I showed you the other day, 107146, where we see a nice face-on disk. And this gives us the feeling that, hey, we're really starting to confirm all of our preconceptions. And it went in spades when we saw HL Tauri, which I showed you the other day. And not only do we see it, but we see the gaps exactly as we expect to see. And as I said before, it's not that there is going to be a planet in all of those gaps. It may also be gravitational resonances that open up those gaps. There are certain gaps, say, within Jupiter's rings or within our asteroid belt that open up because of gravitational resonances. So some of these can be gravitational resonances, but this is like amazing stuff compared to what we had 25 years ago. So, thinking about our solar system and how it stacks up to others, we have lots of dust disks being found, okay? We have asteroid belt and Kuiper belt size things found. We even have things much, much further out. We have belts out at hundreds of AU instead of down at a few AU or at tens of AU. Okay, so we're seeing a variety of sizes of all these things. Of course, we are looking at stars that are at different stages of their lives. To find these disks, we're looking at early stars. Okay, stars that are millions to hundreds of millions of years old. Very important to recognize that the stars in Orion are about 2 to 3 million years old. And I know that's old, that's really a long time for you and I. It's nothing for a star. Our sun is 4.5 billion years old. All right? The formation of planetary systems happens on timescales of tens of millions to hundreds of millions of years. So if we want to see these disks, these remnant debris disks around stars, we look at it, and if the star is a billion years old, that debris disk isn't going to be there. So all of these observations focusing on these disks have to look at stars that are like less than a few hundred million years old, and preferably down in the tens of millions to a few millions of years. So we're looking in the star-forming regions where stars have just been born. Okay? Now you may ask, how can we tell that they're less than tens of millions of years old? Well, we can do that by age dating the most massive stars. Those O stars in Orion, they're not going to live more than 50 million years. Probably not more than 25 million years. They're going to explode as supernovae in tens of millions of years. So the fact that the O stars are there, and all the stars generally form about the same time, as best as we can figure, that means that those stars have to be millions of years old, because those O stars are still alive. Okay? So that's how, and that and a variety of other ways we can use to age date how old the stars and the star clusters are. All right, and we're seeing these disks when we're seeing substructure within the disks. All right, well, that's great. Okay, so far, big thumbs up for all our ideas. We're really happy. Then we start discovering planets. All right, now how are we going to discover these exoplanets? It's actually not that easy, because this is a really, really wimpy star. It's a pathetic 15th magnitude star. Now, when I say 15th magnitude, you should think to yourself, all right, well, 0th magnitude, 5 magnitudes, 5th magnitude is 100, factor of 100. 10th magnitude is a factor of 100, that's 10,000. 15th magnitude, that's a factor of 1,000,000 fainter than a 0 magnitude star. Wow, this is a really, really faint star. It's also one of the closest ones. It's Proxima Centauri. It is, in fact, the closest star. But you can see when you take a picture of it with Hubble that you're trying to look at the faint stuff and you're really trying to get details, the star blows out. Okay? How are you going to see a planet which is deep down in here next to that star when the light of the star, even of a wimpy 15th magnitude star, blows out across your detector? All right? So it's very hard to see the light of the planet directly. Most of our observations of planets are going to be indirect. We're going to find evidence for them. All right? What we're going to use is that Doppler shift. Okay? We can find motion by looking at that Doppler shift to the spectral lines. Okay? If it's heading towards us, they will get blue shifted to shorter wavelength, away from us, longer wavelength, red shifted. Okay? So, think about it. We've got a planet and it's orbiting a star. So if we were able to measure the light of this planet, as it goes away, if we're down here, okay, as it goes away from us, it would be red shifted. And then it comes around here, it would be blue shifted. And we could see a red shift to a blue shift, a red shift to a blue shift. But we can't measure the light of that planet, okay? It's all lost in the glare of the star. However, we remember Newton's laws. For every action, there's an equal and opposite reaction. That's like Newton's third law, right? I don't know, who teaches physics? Right. Is that the third law? Good, okay. All right, therefore, the star itself will have a reaction to the planet, and it will wobble slightly. Remember when we saw Pluto and Charon yesterday, that Pluto was also orbiting the center, and Pluto and Charon were commonly orbiting their center of mass. Well, the center of mass in this system is going to be within the figure of the star, but it won't be at the center, it'll be slightly off-center, and this will wobble around that center of mass. It will produce a very, very small blue shift and a very, very small red shift as that planet orbits. Okay? All right. So could we possibly measure it? Well, in the 1990s, the answer became yes. Before the 1990s, it was no. All right? Now, the way that they did this, and I was at Berkeley when Jeff Marcy had figured this out, was to take the spectrum of a star like this and then overlay on top of it a known spectrum. Okay? And what he did is he actually put iodine in front of the detector so that the iodine spectrum would get imprinted on top of this. The iodine spectrum, because it's sitting there at the telescope and not moving, would have fixed lines. It's like overlaying a grid of lines on top of this, and then you can measure differentially the measurement from here's where the iodine line is, and here's where the spectral line of that star is, and you can do a better differential measurement than you can do an absolute measurement. So by overlaying a grid of iodine lines on top of the spectrum, they were able to very, very finely measure the motion of the star. And that is the trick that allowed them to detect the wobble of stars. Now, of course, when you see that wobble of the star, it could be due to the star's envelope expanding and contracting, all right? But you need to see the periodicity of it in order to measure the planet, all right? And they were able to measure that. Okay, you've seen this one before. So here are the measurements that they got for a star 51 Pegasi, all right? Jeff Marcy and his postdoc Paul Butler. And so, measured in velocity units, positive velocity, it's coming towards us, blue shift. Negative velocity, it's going away from us. All right? And we see a variety of things here. Now, this doesn't make much sense to you until you fit a sine curve to it. A sine curve that passes through all that variety of points. And it makes even more sense when you do a periodogram, take all those sine curves, take all those points into one period of it, and you get it looking like this. That's pretty convincing that you've got a sinusoidal motion of this star, all right, due to the fact that a planet is pulling on it. Now, let's think about this. What is going to produce a large signal here? Well, first of all, you have to have the bigger the planet, the larger the mass, the more gravitational pull. So you'll find bigger planets first, right? The largest planets will be the ones, so the Jupiter mass planets are the ones you would find first. Also, if it's farther away, gravitational force goes as 1 over r squared, it's going to have a weaker force, whereas if it's closer in, it's going to have a larger force. So, if you think about it, the first planets you should discover should be these giant Jupiter planets in really close to their star. And do we have any of those in our solar system? No. We actually have the giant planets further out than the smaller planets. But what did they discover? They discovered where's the Jupiter? Where's the mass? A 4.231 day orbit for a planet that had half a Jupiter mass. A 4-day orbit for a half Jupiter mass planet. This is a Jupiter in right up next to its star. Okay, we're talking Mercury has 88 days in its orbit. Okay, this is much, much smaller of an orbit than Mercury's, and it's a Jupiter mass planet. Mind blown. Okay, not what we were expecting, but if you look at the way we're detecting them, exactly what we should be detecting first. So we're biased in our observations that we really should be detecting these first. We just didn't even know they existed. These are what we call hot Jupiters, okay? And so the mass of the planet is determined by the amplitude of the signal here, and the period here gives you that, and you can work out the mathematics of it. We started to discover more of these, all right? This one has a relatively beautiful sinusoid, which indicates it's on a mostly circular orbit. That's why this eccentricity value here is very close to 0. All right, that tells you it's a circular orbit. This one, one of the next ones discovered, 16 Cygni b, has a period of 2 years. All right, has a mass of 1.7 Jupiter masses, but you can see it's got a very up and down, up and down. That indicates that it's got a highly elliptical orbit. Okay, all right, because in an elliptical orbit, you go through perihelion very quickly, and then you spend a lot of time out at aphelion. And perihelion's quickly, and aphelion slow. So perihelion swoops past it, zoom, and then goes out to aphelion. Goes out to aphelion and back into perihelion and zoom. All right? So the shape of the curve, as well as its amplitude and its width, gives you all the features you need to know. So now we have a Jupiter mass planet. The 2.2-year period, that's reasonable, okay? That's getting out to a distance, but it's got this highly elliptical orbit. Does Jupiter have an elliptical orbit in our solar system? No, it has a circular orbit, okay? All the planets have roughly circular orbits. This one has an orbit characteristic more of an asteroid or of a comet. All right, so we're finding, wait a minute, we're getting elliptical orbits. Elliptical orbits aren't stable. You bring a giant Jupiter on an elliptical orbit, it's going to scatter things across a wider range of the solar system. I mean, Jupiter scattered things and it's just on a circular orbit, right? And it scattered a lot of things. Right? If a Jupiter passes by an Earth-sized planet in an Earth-sized orbit, that Earth-sized planet, I'm sorry, we're kind of tiny. We're going to get scattered around. So a lot more scattering is going to happen in this type of system. Not only can we see individual planets, but we can start to look for multiple planets using this technique. This is the radial velocity technique. And here we can see we've got a nice sine curve fitting to this, but the sine curve itself sort of does a sine curve. And that's the combination of 2 different sine curves, indicating the presence of 2 different planets. So we break down this sine curve into the B component, which has a nice tight short period, and a C component, which has a much longer period. All right? And from this, we can definitively say there are 2 planets in this planetary system. And it's not just 2, we don't have to stop at 2. If you have enough data, enough precision data, you can pull out more and more planets from these systems. We have multiple planet systems. All right, so the radial velocity method worked really, really well for the first decade of our extrasolar planet exploration. But there's a problem with the radial velocity method, that you have to observe for multiple orbits, right? You have to see it go up and down and up and down and up and down, which means you are biased towards short period orbits, right? If you have Jupiter, how long does Jupiter take to orbit the sun? It's 11 years, right? About 11 years. And if you want to see a Jupiter in a Jupiter-sized orbit, and you want to see 3 orbits of that, how many years do you have to wait? 30 years, okay? You've got to wait several decades to see a Jupiter in a Jupiter-sized orbit. Will we ever see that? Well, not in the lifetime of a graduate student, which is really the time that it takes to do these type of things, right? You need to get your graduate student years and your postdoc years, and if you don't have a result by the end of that, yeah, your career's in trouble. Okay, so you need to actually go find if there are other methods you can use. So we found a lot of hot Jupiters. We found a lot of, got down into some lower mass planets, but the planets we were finding were all in Earth-sized orbits or less. Okay? We're not finding things way out. I think there was one in like a Mars-sized orbit that I remember from the radial velocity method. Now we have to look, all right, what other methods can we use to find these planets? Well, if a planet passes in front of its star, then that planet will block out the light of its star. And if we're measuring that star's light really, really carefully, we can't see that planet, but we could measure the change in the brightness of that star, right? Matter of fact, we've done this in our own solar system. All right, how many people remember the transit of Venus a few years ago? This is an actual photograph of our sun, colorized obviously, with the planet Venus passing in front of it as it did from our point of view in 2012. Okay? For the transit of Venus. And they got some really cool photographs of it going through. I think the coolest photograph was this, you know, where you got an airplane. And this is something I found on one of the websites going, oh, we got the most amazing transit of Venus. But the point is that the light of the sun was blocked out by the light of Venus, by the geometric figure of Venus, and therefore the light of the sun dropped by just a percent or so. All right? So, what we need to be able to do is measure the light of other stars really, really carefully and look for these periodic dips. All right? That the light is going along like this, and then it dips, and then it comes back up. All right? It's going along like this, and it dips, and it goes back up, and does so in a periodic fashion. In that way, we can discover as many small planets as we have the sensitivity in our light and our photometers to measure the light. Were we able to do that? Yes. Here are some example light curves from the Kepler mission, all right, in which we're seeing the light drop down and drop back up. And so here's the drawings that they gave. So here's the relative geometric sizes of the planet versus the size of the star that would produce these various light curves. All right, these were some of the first ones, Kepler 4, 5, 6, 7, and 8. Again, finding these short period planets, because those are the first ones that you're going to find with this method. Their periodicities come up faster, all right? So the Kepler mission, what it did is a NASA mission to stare at this field of the sky out in the constellation Cygnus over and over and over. And all it did was stare at that field in the sky, measured the brightnesses of 170,000 stars over and over and over, creating a time series of those star brightnesses. All right, it was up there for 4 years, and this is the view of its field of view in the sky. Now, it had a sensitivity of 10,000 to 1. It could measure the brightness to 1 part in 10,000, which is like looking at this theme park display and being able to tell you that, oh, there's a light bulb out in there. Okay? You got 10,000 lights here. If one of them turns off, the Kepler would have been able to measure it, okay? In aggregate. All right. So here are some of the Kepler observations. This is a diagram of the size of the star versus the size of the planet passing in front of it. I think this was released when they reached around 700 discovered objects. The Kepler ability has greatly increased the number of stars that we've been able to see. We now have over 800 stars observed from Kepler, as well as about 3,000 more candidates. Unfortunately, the Kepler mission, after 4 years, had a problem with its reaction wheel. Its reaction wheel got stuck and could no longer point as precisely as it needed to do these precision observations. So the Kepler mission stopped after 4 years. So it was able to get all of its primary mission. Its primary mission was intended to be 4 years, but we were hoping we'd get 8 years out of it. We didn't get 8 years out of it, so sorry, the Kepler mission stopped there. Now, it is 11:35, and I can stop here and let you guys go for lunch, or I can finish up this and we'll just take our lunch hour a little later. Which would you guys like to do? She says finish now. How many people say, all right, finish now or go to lunch now and we'll finish later? All right, so how many people say finish now? How many say finish later? And how many don't care? Well, doesn't matter. All right, so looks like the majority is for finish now. I will punch through the rest of this. All right, so we've got the radial velocity method. We've got the transit method. Now the transit method requires that a star pass in front of a planet pass in front of its star from our point of view. If it's orbiting like this, will we ever see it in the transit method? Absolutely not. It has to be in that very, very thin plane where it's edge onto us, which means that like about 1 in 100 stars is going to be able to do that. So it's a low probability, all right? The radial velocity method, again, is strongest when it's edge onto us, but it can be seen at most angles. If it's 90 degrees to us, we get no signal because the radial velocity isn't effective. But, all right, so we have to add in statistics when we're talking about the numbers that we see. Finally, the third method that I want to talk about is direct observations of those stars, of those planets. And it's hard enough to actually resolve a star. Just to let you know, this is Betelgeuse here. This is Hubble's image of Betelgeuse, and one of the first images to resolve a star as more than a point of light. Okay, stars are so small and so far away, they're actually kind of big, but really, really far away compared to their size, that even in Hubble, their physical size is less than 1 pixel. All right? Betelgeuse being a supergiant star, all right, Hubble was able to resolve it. First picture ever to resolve a star is more than a pixel. All right? Why? Because it's a supergiant star. Okay? So if this is the size of the star, this is the size of Earth's orbit, this is the size of Jupiter's orbit. If you take Betelgeuse and put it where the sun is, Mercury, Venus, Earth, Mars, the asteroid belt, and Jupiter would all be orbiting inside the size of that star. It's about 1,000 times the diameter of our sun. So that's a really big star. That allows us just to see the stars. This gives you an idea of how hard it is just to see the stars, much less the planets around it. Did you have a question?
Yeah, the Dimian method of
Yes.
finding the planets. Do stars rotate on axis?
Yes.
Is it possible that they could have like spots like our sun has that it would throw it off?
Give me a fist pump. Yeah! All right, that is something I did not mention, but one of the problems with looking for planetary planets is that there can be other confusion. Stars themselves are a little bit variable. For the very cool stars, they can have rather large star spots. Okay, can't call them sunspots because they're not on our sun. They can have rather large star spots, and if those star spots rotate in front of us, that will also decrease their brightness. So the data analysis to try and pull out these Kepler planets is really extensive to look for these type of observations, these type of false positives, we call them. Okay, things that look like a planet but aren't really a planet.
We can detect which direction stars would be rotating in each direction, right?
It would be really hard. I suppose Kepler does not have that capability to measure the Doppler shift down to that point where you could measure the rotation of a star. But yes, for some stars we can, for stars that we study in detail, we can try to measure a Doppler shift to see their rotation. But remember, when you're looking at the star and it's rotating, if it's rotating like this, you're seeing both the blue shift here and the red shift here at the same time. So trying to differentiate between those is difficult, but there are techniques that can get that. It's called Doppler broadening. Okay? All right. All right, so we're trying to get into trying to see things. So it's really difficult to see in close because of the bright of the star. We have to block it out. So here is one star Fomalhaut that we're going to try and look in. All right? And so here's what we see in Fomalhaut. And I know what you're thinking. You know what that is, right? Yeah, it's the Eye of Sauron from the Lord of the Rings movies, right? No, it's not. It just has a wonderful resemblance to it. It is actually a picture of a dust ring around Fomalhaut, or a debris ring around Fomalhaut. So this is where Fomalhaut is located. This is the part that has been covered up by the coronagraphic mask. You'll see all that striations, all right? That's noise produced by the coronagraph, okay? So, why is this an interesting thing to look for? Because of the next slide there's the scattered starlight here, and there's no data out here. You'll notice there's some sharp edges here. That's just because there's no data. So why was Fomalhaut an interesting place to look? Well, because the ring is not entirely centered on the star. The center of the ring is actually a little bit over here, all right? And we find that it's not totally centered on the star, which means there must be some gravitational influence pulling it slightly off center. All right? It has to be some gravity. So when looking at this is out at about 120 AU, all right? And they did the dynamics of it, and they calculated, well, if you had like a 3 Jupiter mass planet, that would be enough, and it was orbiting just inside the ring, or outside the ring, it would be enough to do the gravitational perturbation. So they went and they said, what are we seeing? Oh, look, there's a bright spot right there. Could that be it? Come on. Nope, that's a background star. Oh well, all right. They looked and they scared and they went through it, but right here they found a little dot. And that red dot, as they watched it over the years, moved to this spot. Oh, an amazing red dot moving across the sky. But of course, like we saw with finding Pluto, you see it move, you measure it, you calculate its orbit, and this was on a proper orbit for being something that would perturb the ring. What you're looking at here is the first optical pictures of a planet around other stars. All right, the first visible light images of a planet around another star is red dots, okay? 3 pixels wide. Oh, exciting! Yes, but it's a really important intellectually red dot, okay? A lot of things at the edge of astronomy are just small little dots, okay? But they're important dots once you understand it, okay? So, we're able to actually see, in a few cases, planets around other stars. But there's a problem with this red dot, okay? And that is that it was too bright. For a 3 Jupiter mass planet, at the distance of Fomalhaut, which is only 25 light years away, and at the distance from its star, it wouldn't be reflecting that much light. It wouldn't be as much light as Hubble had discovered. So the folks who found it said, well, what actually is happening is it's still in formation, and so this is the planet, and there's a disk of material collecting onto this Jupiter mass planet, because when Jupiter mass planets form, they also get disks of material. They get sub-disks within the major disk, okay? All right, so that material around here would help reflect the light of the planet, which is over here, and you can see the dust ring depicted back there, and make it brighter, all right? Now, I will tell you that this group, the ones who discovered this, were at Berkeley, where I did my postdoc, where I did my PhD, and then a group at Princeton came in and said, no. And I did my postdoc at Princeton, so I have affiliations with both of these groups here. And the folks at Princeton said, no, that's not what's going on here. It's just a dust cloud. It isn't a planet altogether. All right, and they said, oh, we've got some Spitzer observations that sort of indicate that. And then the Berkeley group comes back and says, no, we did follow-up observations with Hubble. We found it, it's moving on this, and we really do believe it's a planet. We know there has to be some dust, but there's a planet at the center of the dust. And so you got Berkeley and you got Princeton going back and forth, and it's really been fun to follow it. Most people accept the idea that it's probably a planet. We will need higher resolution infrared observations to truly settle the question. High-resolution infrared observations. Didn't we hear about a telescope that's going to do that? Yes, the James Webb Space Telescope will be required to play referee and get people in Berkeley and Princeton to play nice together. Okay, they all play nice together. I just like to tell it as a soap opera. Okay, however, this wasn't the only planet observed directly. In the same issue of Nature magazine that this result came out in, also there was this result for the star HR 8799, where they did interferometry from the ground with a Keck telescope, adaptive optics, infrared views of the star HR 8799. This speckle here comes from blocking out, removing the star HR 8799, and they found 1, 2, 3 planets around HR 8799. Again, 3 really important red dots, the first infrared light photographs of a planet on other stars. So we're moved from indirectly observing these planets to, in 2008, we can finally say we've actually seen the pixels from a few planets. 4 at this point, it's gone up to maybe 7 by now. All right? What we can then do with Hubble is go back into the Hubble archive. This was a picture from Hubble from about 7 years earlier. We go in, we subtract out the light of that star using new computer techniques, and we can recover those 3 planets as they were 7 years earlier. That gives us a longer baseline for their orbits, helps us calculate and understand that planetary system even more. That Beta Pictoris disk, well, some folks at the time, 1 week after the other results came out, said, oh, we got another planet too, but we can't see it because it's now in front of our star. We got to wait till it comes back. They did see it when it came back, okay? So, we've gone through a variety of detection methods. There are a whole bunch of other ones, including gravitational microlensing that are very difficult to explain, and pulsar timing, etc. But I've given you the 3 major ways, 3 exciting ways that we have seen planets. All right? And so when we look at these planets around other stars, we've got 1,564 confirmed planets. Planets that the community has said, we've got enough evidence, we really believe that we've got these planets around these other stars. When there's indirect evidence, you have to have a confidence level. All right? We have another 3,771 candidates. Most of these are from the Kepler mission. Because the Kepler mission was only up for 4 years, it didn't have enough data to say, absolutely, we really are confident in this. But you know what? The estimates are 90 to 95% of those are almost assuredly planets. Okay? So we got a 90 to 95% confidence. So I'd say there's another 3,500. We got about 5,000 planets we know about. That's really cool. Okay? We have a whole new era of studying planetary systems. All right? We've got lots of multiple planet systems, especially with Kepler. Kepler was able to detect things down to Earth size. We have one planetary system, Kepler 186f, in which there are 5 Earth-sized planets. All 5 of the planets around Kepler 186 are between 1 and 1.4 times the radius of Earth. How cool is that? We've got a planetary system with 5 potential Earths. And the 5th one, Kepler 186f, is out at a distance. It's a red dwarf star. It's out at a distance such that there could be liquid water on the surface of that planet. It's a 1.1 radius size planet. It's at the correct distance where, if it has an atmosphere and if liquid water is there, liquid water can exist on its surface. So we have a potential Goldilocks, because most of the planets we've discovered are too close and they're too hot. All right? There are a couple that we've discovered that are way out and are too cold. Not too many of those, because our detection methods are biased towards finding close-in planets. All right? There are some that are out there that would be too cold. We're looking for that Goldilocks planet that is just right, where we get liquid water. As we said earlier, we're looking for energy, carbon, and water. Energy and carbon are plentiful. Is there water out there on this? So, I'm sorry, I forgot to get the most important thing, is that in doing this statistics, I talked about the statistics of seeing this, where we can only see things that are edge on with the Kepler, okay? We see things better that are edge on with the radial velocity. Various other techniques have their biases. So we do statistical samples, we add in the observational biases, we get at least 30% of sun-like stars having planets, and overall, we get an average of 1 planet per star, which means if there are 100 billion stars in the Milky Way galaxy, there are also 100 billion planets in our galaxy. All right? That's a lot of planets for us to go. We're going to keep ourselves employed for quite some time studying that. All right? So we have begun looking for them. All right? And you will see sometimes things, people talking about an Earth-like planet at last. And I want to say that that Earth-like phrase is wrong. All right? We want to find planets that have Earth-like characteristics, but we have no idea if they're actually Earth-like in terms of that they have land masses and water and atmosphere and clouds. You will always see drawings that make it reminiscent as if it could be another Earth. We only see with the Kepler, we see the radius of it, okay? And from that, and we see the orbit. And from that, we have to imagine what it could be like. Right now, we don't know whether their characteristics are truly Earth-like, but there is a way we can find out, okay? And the way we can find out goes back to this transit of Venus. So this is Venus, this is the sun. And you will notice that out here, you see this little thin yellow edge of Venus. What is that? That is the light of our sun passing through Venus's atmosphere. So some of the light of the star is passing through the planet's atmosphere during a transit. Which means that if we take a picture during transit and another picture not during transit, we will get the light of the atmosphere in one and not in the other, subtract the two, you get the light of